Good morning, good afternoon, good evening, wherever you are. It's my real pleasure again to resume this W2S seminar. So last week we didn't have a seminar because we are hosting this conference on spintonics and magnetism, which went pretty well, I would say. So I'm really delighted to welcome Professor Vincent Cros from Khalle's lab. I think he really does not need any formal introduction. He is very, very well known in the field of spintonics and magnetism, has done really phenomenal work. I also welcome Professor Albert Ford to this seminar. I see he is there. I think Vincent and Albert have a very long standing collaborations, and I'm really glad to welcome him as well. And I also welcome all other participants. So thank you so much for joining. Because of you people, somehow we are managing this seminar. It's, I think, already 73rd seminar today of W2S. So Vincent Cros has obtained a doctoral degree in material science in 1996 from Université Denis Diderot in Paris, in France, where he studied the magnetic and transport properties of magnetic multilayers and nanostructures under the supervision of Professor Albert Ford. During the first year of his PhD, he worked on interlayer exchange coupling at the Institute for Festkörperforschung in Jülich in Germany, supervised by Professor Peter Grunberg. After receiving his degree, he worked 1 year as assistant professor in the University of Paris, where he studied the spin-dependent Coulomb blockade effect in single electron devices. Then he joined the group of Professor Miranda in University Autónoma de Madrid, Spain, as Marie Curie Fellow postdoc to investigate the mechanisms of surfactant-assisted growth of magnetic multilayers. So I see you have worked with both the Nobel Prize winners in Schema. It's really nice. So in 1998, he was appointed as researcher by the French National Science Agency, that is the CNRS, at the joint CNRS-Thales Research Lab at Palaiseau in France, in the group of Professor Albert Ford, where he rapidly focused his research on spin transport phenomena and created a team working on this topic. From 2000 to 2005, he performed among some pioneer investigation of spin transport phenomena, and notably on the first experimental demonstration of spin transfer induced magnetization reversal of magnetization without any magnetic field. Then he extended his work to high frequency magnetization dynamics induced by spin torque and its related radio frequency properties of spintonic devices. His current research interests include noise properties, nonlinear phenomena, and synchronization of spin torque oscillators, spin transport dynamics generated by spin orbit torques, and more recently the physics of magnetic fermions in nanostructures, which is the topic of today, and their potential application in a novel generation of spintonic devices. He is author about 220 articles in scientific journals and filed 23 patents on spintonic devices. In 2013, he received the Carnot Prize from the French Academy of Science for his work on spintonics. So thank you so much, Vincent. I really welcome you to this seminar. I really appreciate that you found time from your busy schedule. We will all benefit from your lecture. I just like to announce two small things. Maybe there are new participants. During the lecture, we don't take any questions. So if you have a question, you can kindly write in the chat box or raise your hand. At the end of the lecture, we will take all the questions one by one. And at the end of the lecture, I would request you to switch on your camera to take a quick group photo. And then we will take the questions, and finally we will present a memento and we'll end. Thank you so much. So it's all yours. And again, I like to thank from all my organizing team of W2S, myself, my co-convener Rajbhushan Singh, team members Puspendra, Shakti, and others. So it's all yours, Vincent, and please start now. So you can start sharing now.
Okay.
Yeah, I see it.
So, okay, perfect. So first, thank you, Professor Vidanta, for the kind introduction, and thank you very much for you and the organizer for inviting me for giving this seminar. I have to say that I would have really liked to be there with you to present, to make this presentation, but okay, that's life. We have to adapt ourselves to the consequences of the pandemic, but also on the other hand, it gives also an opportunity to open the audience more broadly and to share, which will be my objective, some results and some ideas about the wealth of this relatively new topic that corresponds to non-collinear spin textures in magnetic multilayers. And in fact, my initial plan was really to focus for this presentation on the very recent results that we have obtained in the last couple of years, mainly on skyrmions and chiral spin texture, but also in two-dimensional, but also going toward the third dimension with a novel type of, let's say, three-dimensional texture, like hybrid chiral texture, or even what we call skyrmionic cocoons. But you told me that there might be some people in the audience that will not be so familiar with this magnetic skyrmions, and so I will start with a more general introduction. I hope that will be not too simple for most of the people in the audience. So I am Vincent Cros from this CNRS Thales Joint Laboratory in Palaiseau in France, but obviously all the work that we present has not been done by me only, and I would like really to acknowledge the contribution from students in our lab: Yanis Sassi, Mathieu Grelier, William Legrand from postdoc, Sachin Krishna, Sogata Malik, Fernando Arras, Eric Burgos, and Titica Srivastava, and from permanent people, and in particular the crucial contribution from Nicolas Reren, and also, of course, from Albert Fer, that is in the audience. Thank you, Albert. But also, this work has been done in collaboration with many other groups. I would like to emphasize the really nice work with Beamtime Soleil in the Synchrotron Soleil in France from Nicolas Jaouen, and also some recent collaboration with Felix Büttner, Germany, Jovan Kim from C2N, and Vincent Jacques from Montpellier. So just to give a little bit the background of all this research, I mean, this is part of this relatively new topic in spintronics that came out about 10 or 12 years ago, that is called today spin orbitronics, and that aims at exploiting the spin-orbit interaction, not only the exchange interaction, exploiting the spin-orbit interaction to open new avenues, new ideas for the basic research, but also for potential technology. And this spin orbit can be divided in three branches. Two of them concern the use of the spin orbit interaction in order to convert efficiently charge current into spin current, or vice versa, and it can be done in the bulk of the material, but the so-called spinel effect or inverse spinel effect, or more recently at the surfaces like Rashba interfaces or surfaces, or even surface state in topological activity. I will not talk a lot about that today, even though I will speak in one part of the presentation about optimization of the spin orbit torque that can be used to move magnetic skyrmions. Because the third branch of the spin orbitronic topic groups the use of the spin orbit interaction in order to generate this antisymmetric exchange interaction called Jacobson-Schema interaction, in order to stabilize new magnetic configuration, and among them there are the magnetic skyrmions that will be the main focus of the presentation today. So what is the magnetic skyrmions? Most of you probably knows, but let me start by this. This is a schematic drawing of skyrmions. You see we have spins pointing outwards on the outer part of the skyrmions, and then there is a whirling of the magnetization, and at the center you have a spin that is pointing downward in this case. So why did I put this picture? Is because skyrmion is a soliton, and a soliton, like this wave, is a wave packet which moves through a dispersive nonlinear media without changing neither its shape or its velocity. So it's a very interesting property of the soliton that they can behave like as you will see later, like particles. But the difference between other type of solitons, like the wave, the clouds, the electrical pulses in neurons and so on, are solitons, but the skyrmion, they are topological solitons. It means that topologically speaking, they are different from the ferromagnetic uniform state. So, and it brings some of the most remarkable properties of the scan. So, how to quantify this topological nature? In fact, the way to do it is to use this expression that corresponds to the Scarmian number or winding number, that is nothing else than a measure of the wrapping of all the spins that are contained in the Scarmians onto a sphere. And this quantity for the Scarmians is quantized, is equal to plus or minus 1. And this non-trivial topology of the Scarmians make that they are, I mean, it's difficult to transfer them a state with the Scarmians to a state without Scarmians. So they bring some robustness to the Scarmian to eternal perturbation or to thermal energy from outside, but also it's this non-trivial topology is really the basis of the field that is called emergent electromagnetism. Because of this topology, you do have emergent magnetic field or emergent electric field associated to the Scarmians that brings a lot of new and very interesting properties to be studied. As I said, the Scarmians, they are soliton because they behave like particles in a 2D media, and you will see at the end of my presentation that we even want to push this to the third dimension, but they behave like particles, so they can be moved, they can interact, they can be counted, and so on and so on. And also, they can be extremely small as a few atomic lattices parameters. So it means as soon as you have the idea to store or to treat the information using magnetism, the magnetic Scarmians are probably the ultimate magnetic configuration. Okay, there are some more stringent definition because there are still a lot of debate of what is a Scarmians, what is a real Scarmionic bubble or magnetic bubbles. I would say 3 points that make this distinction. The Scarmians, they are not stabilized contrary to the bubbles only by that dipolar coupling. So it means that you should have a continuous rotation when you go throughout the core of the Scarmians. And very importantly, they have a fixed chirality. And all of this, in fact, comes from the essential role of the Jaroszewski-Moria interaction in the stabilization and for the property of the Scarmians. So this, let me say a few words about the Jaroszewski-Moria interaction. So here you have the Hamiltonian that corresponds to the systems, and where you recognize with this dot product the exchange interaction, which favors a collinear configuration of neighboring spin, either parallel or anti-parallel. And you do have this Jaroszewski-Moria term with a cross product between neighboring spins. It means that this term favors a tilting of neighboring spins around this vector. And this, in fact, was first introduced 60 years ago by Jaroszewski and then rapidly after by Professor Moria in order to explain the weak ferromagnetic contribution, the weak ferromagnetic component in a non-centrosymmetric magnetic insulator with super-exchange. And for quite a long time, it was supposed that this antisymmetric exchange interaction will be important only for this magnetic insulating materials. And in fact, Albert Fert, and together with Professor Levy, extended this to metals at the beginning of the 80s, using for the description the RKKY, so indirect exchange interaction mechanism in spin glasses, in order to explain spin glasses that contain heavy material impurities, and so the interaction, electronic interaction between neighboring spins can occur when going through this impurity with last spin orbit coupling. Basically, can be described by adding also in the Hamiltonian a term that has exactly the same form as the Jaroszewski-Moria for the bulk materials. So this antisymmetric term is what do you need? What are the basics of the principal ingredient to get this anisotropic exchange interaction? You do need, as I said, the spin orbit interaction, and you need a break of the inversion symmetry. And there are different ways to obtain this break of inversion symmetry. In the bulk materials, when you have a break of inversion symmetry in the structure, crystallographic structure, you do have this configuration. So you see the D vector is pointing along the unit vector between S1 and S2. And in the case that we are interested in, so interfaces and thin films, the D vector, as you see, is perpendicular to the plane formed by S1 and S2. And this now famous drawing of the interfacial schema interaction is nothing else than the one described. Okay, just one word about, I think this is important, that the topology and chirality are two different quantity and characteristic, because you can have different chirality or different direction of the Gerich's schema vector. You do see here again for the interfacial Gerich's schema case, you can stabilize what is called nail scarnons or hedgehog scarnons. And if you have a bulk break of inversion symmetry, you will stabilize some block scarnons or vortex scarnons. So you see they are different in terms of the way the whirling is occurring, but the topology is the same. In both cases, we have the topology equal to -1 in this case. So just a few words about why this Gerich's schema is important in today's magnetism property in nanomagnetism, let's say. If you consider, for example, a stripe with perpendicular magnetic anisotropy, two domains, up or down, are separated by block domain walls if you have zero Gerich's schema interaction. But then if you increase, if the Gerich's schema interaction increases, then the nail domain wall, so this configuration inside the domain wall, will become favorable. And if you keep increase the Gerich's schema interaction, then you have even the stabilization, the most favorable configuration becomes a spin spiral state with a given chirality that is directly linked to the sign of the DMI interaction. And this is in this region of very large Gerich's schema interaction that the first pioneer observation of dense Skyrmion lattice, either in the reciprocal space in neutron scattering experiment, in MNSE, or in the real space in Japan, in this alloy that are part of the B20 crystal family, so non-centrosymmetric crystals. But then there have been also some experiments on thin films, ultra-thin films, done in Hamburg, in the group of Professor Wiesendanger, when, for example, they observed by spin polarized STM that if you put one monolayer of iron on tungsten, they can clearly image by this technique a spin spiral state with a given chirality. And rapidly after, by applying very large magnetic field and at low temperature, they could even get some system where this spin spiral can be transformed into a Skyrmion lattice space. So this is for the case of very strong Gerich's schema area above this threshold value. But if we want to have isolated Skyrmions, we are more interested in this range of Gerich's schema interaction that is below this threshold value for stabilization of lattices. Okay. So let me now say a few words how to engineer the property of magnetic multilayers to stabilize the Skyrmions. And this is where, in fact, we start to be very interested in this topic now about almost 10 years ago, because we thought that using our expertise and experience in spintronics in the preparation of thin films and multilayers, we could prepare a system like this with a very thin magnetic layer in contact with the heavy materials in order to get these two ingredients, break of inversion symmetry and large spin orbit coupling, with the idea to stabilize Skyrmions not at low temperature and very large field, but at room temperature and, if possible, zero magnetic field or small field. And the main advantage of this approach compared to a study in the bulk materials is that we have multiple possible associations in terms of materials. We can change both materials, but we can change also other parameters, the PMA, the number of interfaces, and so on and so on. And this is what Bertrand Dupé, that is a theoretician working in Belgium now, called the Skyrmion à la carte. So it's like to make some cooking with the parameters in order to stabilize and control the property of the Skyrmions. And based on this idea, we had in mind that maybe once stabilized at room temperature, these very small topological spin texture, the scanons, they can be used as bit of information in some conceptual devices that we call Scannon restrict memories. And you see, you can store the information by the presence or not of a scannon that can be moved by spin transfer torque, as I will show later. This was in 2013, only micromagnetic simulation at 0 temperature. And in fact, it starts to become reality rapidly after. And we could observe about 3 years later, the first room temperature scanners with very small sizes, like less than 100 nanometer. This is an image obtained in one of the multilayer I will show later by scanning transmission X-ray microscopy. And you do see here some scanners in the middle of the chart. So I have no time now to make a kind of state-of-the-art, very detailed state-of-the-art, because it has really been the subject of research of many groups in the world with many different systems. And in fact, I like to show this image I took from this review paper. You see there are very different systems at room temperature with different sizes, ranging from a few tenths of nanometer in diameter up to a micron or bigger, but all of them, importantly, they have a fixed chirality, so they can be moved by spin orbital, as I said before. So in terms of application, I will not say too much today. I already mentioned this concept of restrict memories. So you can generate scanons, move the scanons, detect the scanons by either a magnetoresistive effect or whole voltage contributions. And this could be really the future for very emergent memories. But I think even more probably interesting are the potential application of scanons in some kind of probabilistic devices or neuromorphic computing, because they really rely on the fact that the scanons are particles in a 2D media or even in a 3D media. And there is a first example, not only concept, but some first example obtained by Matthias Clauy in Germany, this Carmion chamber that can be used to make some probabilistic calculation. Or if you have a combination of different of this Carmion chamber, you can make some neurons and use the fact that you can push scanons and count them as to mimic the behavior of spiking neurons. Okay, so this will be this was the end of my introduction, and now I will go to some recent results that we have obtained in our laboratory about the scanning. And we start with the stabilization of ultra small scanons in ferromagnetic layers. So for that, this was mainly the work of postdoc Fernando Arreras. We use ferromagnetic multilayers like this that we can prepare by sputtering deposition. So they are not epitaxial system, but they are deposited by sputtering deposition. And you see, in this case, we use cobaltarium boron, ruthenium, platinum multilayers. So we have this break of symmetry in terms of the materials that are around the magnetic materials, and you have here the typical thicknesses 1 or 1.5 nanometer. And then we can repeat the number of multilayer of this basic brick in the multilayers. So if you these are magnetic force microscopy images at room temperature, you see that at zero field you do have a warmy state with up domain and down domain, and then if you apply a perpendicular magnetic field, you can transform this labyrinthic configuration into a phase or a regime where you do have a large number, a large density of scanons that can be stabilized. But then if you keep increase this magnetic field, perpendicular magnetic field, you end up with more isolated scanons, and the signal becomes very weak because, in fact, they become extremely small. This is because we really optimize all these parameters, PMA and BMI and so on, to get these scanons very small. And you see, if we make line section across a few scarments, you see, we can have a peak in the statistic for a diameter that is about 20 nanometer or sub 20 nanometer scarments stable at room temperature, which is, to my knowledge, some of the smallest scarments that can be stabilized at room temperature. But then using MFM, there is always the question of about the interaction with the tip, that is magnetic itself. And this is why in the postdoc of Eric Burgos, in collaboration with Soleil Saint-Protron, we use this technique that is called X-ray magnetic holography technique, preparing the very same sample, but then on membrane, and shining coherent X-ray on these membranes. We can have an image in transmission first, and we can make a statistic on a very large number of scarments without perturbation from the tip like in MFM. And from this, we have also a statistic, and you see that again, like in MFM, so it means that the MFM image was not perturbed that much by the tip. We have a diameter that is about 20 nanometer in average. Then a very another issue that came out today in the research for scarments at room temperature is that even if we do not need in multilayer a very large magnetic field, in general we do need a perpendicular field of a few millitesla or a few tenths of millitesla. And for the potential application, this is important to have a no magnetic field. So for that, we prepare magnetic multilayers, in this case platinum, cobalt, platinum, but including what we call the bias layer, composed of symmetric platinum, cobalt, platinum layers, which in fact create an effective magnetic field generated by the electronic interaction between these bias layers and the bottom magnetic layer. And this allows us to create, without field, after saturation, to have the stabilization of magnetic scarments with, in this case, for this parameter, scarments that are about 80 nanometer in diameter, but at strictly zero magnetic field applied. Okay, now I want to go a bit beyond, because talking about the role of the dipolar interaction. In fact, we use not only thin film, but also multi-layers in order to stabilize the carbon, increase the spirality, but there is a price to pay for that. Is that the dipolar interaction, the dipolar field between layers is not negligible, and it brings some new features in this spin texture that can be stabilized. So for that, in collaboration with Nicolas Jaouen, Beamline, and Soleil, we use X-ray resonant magnetic scattering experiments. In this technique, we basically shine X-rays with different circular polarization onto a magnetic configuration. And in this case, we use tri-domain configuration. And you see that then we collect on the camera the off-axis diffraction. And you see that we have two peaks, and these peaks, the distance between these peaks is directly related to the periodicity of the configuration that you are investigating. So in this case, stripe domain, but imagine that you have a Scarmian lattice phase, you will get also some peaks associated to the sixfold, in fact, peaks associated to the Scarmian phase, but then you can measure the periodicity of the Scarmian. But more importantly, what you can do with this technique, you can take the difference between the two, the image with the two configuration, and then you get a dichroic signal. And these colors, the fact that you have two colors here, blue and red, means already that you have do have a chiral spin texture. That is, you have a given chirality. So it brings very rapidly and very straightforward some information about the chirality. And what we studied, it was a part of the PhD of William Legrand. We apply this technique to multi-layers, platinum, cobalt, I think alumina in this case, for 5 repetitions. And you do see what we get on the CCD camera after making the difference between the two polarization. First, we get the maximum of the contrast on this axis and not on this one. And this directly means that we do have nail domain walls and not block domain walls. And second, we see that we have the color, the order of the color, like here the blue, white, red, the French black, means that we have a clockwise, as expected, when we put the heavy metal onto the ferromagnets. Now, if we prepare a sample the same but with opposite stacking order, you see that we get exactly the opposite background. So as expected, we can characterize nail, domain wall, and their chirality. If we repeat it, when we repeat the same with 10 repetitions, we have exactly the same results. But then the surprise was for 20 repetitions, we find that there is no inversion of the dichroism when we change the stacking order. And the reason for that is that in this multi-layer, as I said, if you have a large DMI and a small number of repetition, in this case 5 repetitions, we calculate using micromagnetic simulation that we do have basically the same configuration in every layer, and these are scarmions with chirality defined by the DMI. But then, when you increase the number of repetitions, you do have an increase of the role of the dipolar interaction between dipolar field between layers, and this dipolar field has an opposite action compared to the field associated to DMI from the upper layers. And it means, you see, we start to twist the magnetization inside the scarmion wall or the domain wall here in the top layers. And this effect becomes even more, becomes even stronger with 20 repetitions, where you see that the effective chirality in the top layers is in fact driven by the dipolar fields, and at the bottom they are driven by the combination of dipolar field and DMI. So it means you have opposite effective chirality and even a change of the nature of the wall, which becomes block domain wall or block scarmion in the center of the nucleus. And because in the RMS experiments we probe only the top layers, it explains why we do not have a change of the dichroism when we change the stacking. So this demonstrates the possibility that, in fact, the reality is that we don't have only in large number of repetition tubular scarmions. We do have tubular scarmions, but with a twisted chirality, and that's what we call hybrid chiral texture. And this was the first, let's say, path towards more complex three-dimensional spin texture. I will show at the end of the seminar that we try to go beyond this and create really three-dimensional texture. So let me say a few words about now the recent results on the nucleation and motion of individual scarmions. This is very important, as I said, for the potential application to use this fascinating property of scarmions, but to make them mobile. So this is the main part of the work, PhD work of Yannis Sassi. And what we did recently was to try to control by a current injection the density of scarmions. And for that, we focus on the multi-layer system that is platinum, cobalt, aluminum multi-layers. Okay, so these are MFM images. You do see here a track, and this is a configuration that can be imaged at different perpendicular field after a pulse injection. You see clearly that the density of scarmions, or even the transition from, let's say, strike domain to scarmion, depend on the field that you apply, and for a large enough field, we can have even individual scarmions that can be stabilized. So we could plot the minimum current densities that needed to be injected in the layers to stabilize the scarmions, and we can control also this minimum current density by applying perpendicular. Okay, so message is a combination of current injection, because the nucleation is mostly thermally activated, and magnetic field is the good way to proceed to stabilize the scarmion. And then we can move the scarmion. So again, these small movies that we show are obtained by MFM. So we have an MFM image, we inject the pulse, we do a second image, and so on, and we can make some movies about the scarmion. So we do see scarmions after the nucleation I described before. And okay, here it should have a movie, sorry. So for one current sign of the current that is injected, you move the scarmions to the right, and when you change the sign of the current, you move the scarmions to the left. Then you can increase the see what brings when you increase the intensity of the current that is injected, and these are different movies, and you do see that there is an increase of the velocity as a function of the current density. For this particular case, we reach, because we limit the maximum current injected at about 5, 10 to the 11 amps per meter square. We have velocities about 10 meters per scanner, but these are really the average of a large number of events, and showing that we can increase, and the purpose will be to further increase the velocity, but also not only to further increase the maximum velocity by increasing the current, but also to decrease this threshold. That is also a very an issue today for the motion of the experiments, and to increase the slope here of the velocity versus current density. So what about the optimization of the spin orbit torque for improving this motion and nucleation experiment? So here we show some very recent results done in the postdoc in our group of Sachin Krishna, focusing on the determining a quantitative determination of the spin orbit torque. So that this is a mechanism that is used for the motion of the sternum. So, as I said in the very first slide, spin orbit torque are related to the conversion of the charge current into pure spin current. And these spin currents, once generated, can be used to be transferred onto the local magnetization, in our case, the magnetic current. So, the system that we have investigated is the following. It's very comparable to the one I showed before for the dynamics: platinum, cobalt with variable thickness, and aluminum or copper. We show just after. So we prepare again this multi-layer by spectrum deposition. I have no time to speak about that today, but we have a very nice quality of the multi-layer. We have no, for example, oxidation of this aluminum or copper layer. And then Sachin has done a lot of experiments to quantify by called the second harmonic technique, either the damping light torque, so the one that is very important for the motion, or the field light torque. Okay, so to use, there is basically a measure of the oscillation of the magnetization when it's locked or synchronized to an AC current. Here are a summary of the results. You see these two systems, platinum, cobalt, aluminum, or platinum, copper, the damping light torque as a function of the cobalt thickness. And you see clearly that first there is a maximum, you reach a maximum for the damping light torque that is associated to the optimum thickness of the magnetic layer in order to absorb the spin current that is mostly generated by the spinel effect in this platinum layer. But interestingly, you see that there is a big change, a big difference between the two systems with two different light elements. And this is not only on this damping light torque that the aluminum is very nice. There is also for the field light torque, you see a large increase of the field light torque in the case of alumina, which in fact is associated, I have not, will not enter into the detail, but to the fact that we do have the aluminum also, you have a strong contribution that can come from the Rajba state and the torque that has associated field light torque at the interface between cobalt. And this is proved also by this thickness dependence for the two systems. You see that we almost have no thickness dependence for the copper, whereas there is a strong increase of the damping light and of the field light in the case of aluminum. So this is a signature of a combination of two effects from the aluminum. First, as I said, this Rajba contribution here, but also the fact that for thick enough aluminum layer, basically we kill the spin current that is generated in the top platinum layer, and that could act with opposite effect on the cobalt systems. So to summarize, by doing all this precise measurement, we demonstrate that we have a large increase both of the damping light torque and spin light and the field light torque compared to the state of the art. Okay, so this was for the ferromagnetic experiments and also for the improvement of the motion, but then there is also some very interesting things to do in systems with cancelled magnetization. can be ferrimagnet or antiferromagnetic systems. And why this is important? Because, as I said, the dipolar fields between layers can have, first, it can make this hybrid texture, but also dipolar fields leads to an increase of the size of the scarments, and it is predicted that the minimum size will be obtained in systems with very small or compensating magnetization. Can be this is one effect of the dipolar field. The other one is that because you have this non-trivial topology, in fact, the motion is more complex than just a Newtonian motion, so the motion along the fault you apply, but you do have a transverse motion for the Scarman Hall effect associated to the topology, which is not that good for the potential application. So there is, with antiferromagnets or compensated ferromagnets, you might have a motion that is without this Scarman Hall effect. Okay, and we try to do these studies on two different types of systems. First, I want to talk about the recent work started in the postdoc of Sugata Malik in our group on ferrimagnetic systems. So basically multi-layers containing rare earth elements, in this case platinum, cobalt, terbium heterostructures, where we can vary the thicknesses, we can vary the number of repetitions, and we find that there is in fact, a spontaneous magnetization does exist when we have thicknesses of the terbium that are relatively small, below 0.5 nanometers. And interestingly, in this range of thicknesses, we were able to observe some scarments that can be stabilized in the multilayer. This is shown here by magnetic force microscopy imaging that are in this case extremely difficult to obtain because the signal is very weak and very sensitive to the interaction with the tip. So there has been a huge work of the development of some specific tip to realize this image, but you do see that small scarments in the range of 100 nanometer or less can be stabilized in these multilayers. Also, another work on ferrimagnetic systems is in collaboration with Carlos Rojas Sanchez from Institut Jean Lamour and Michel N. We prepared, Sugata Malik prepared some systems here, like containing both this Scarman multilayer, platinum, cobalt, copper in this case, but then separated by copper from a ferrimagnetic layer that in this case will be used as a large emitters of spin current, because we demonstrate recently in collaboration with Nancy that we have a large spin charge or charge to spin conversion effect in this motion. So this is the thing that needs to be demonstrated. Already we succeed to demonstrate that Scarman can be stabilized in these layers. Then I talk about the ferrimagnetic system, but we had also some work on the antiferromagnetic systems, and it was in the PhD work of William Legrand. And for that, we use the platinum cobalt ruthenium platform. These are the typical stacking of materials that we use. And because we can prepare with this system as a multilayer with a very large Jaroszewski-Moore interaction that is needed again for all these chiral detectors, we can precisely control the perpendicular anisotropy. And what is important to stabilize the antiferromagnetic scanners is to be very close to a compensating effective magnetic anisotropy. And we can very well control the RKKY exchange, indirect exchange interaction through this between two magnetic layers through this spacer layer. And we can get the layer that for which we maximize the coupling to be antiferromagnetic. Okay, so doing so, what can be expected? If you have two layers that have a very strong perpendicular anisotropy, you will have, this is a top view, this is a sub view, you will have two uniform domains, but antiferromagnetic coupled at each position. What happens if you have now a compensated effective anisotropy? In fact, the combination of the Jaroszewski-Moore interaction, the absence of coupling of long-range dipolar fields create a spin spiral state. Okay, and in fact, this is what we try to demonstrate experimentally first. So we prepare a system with two strongly coupled antiferromagnet with compensated anisotropy. And this is the top view of the configuration recorded by vacuum MFM, because the magnetic signal is extremely weak. Again, at each position, we do have an antiferromagnetic copy, but you do see here that we have this spin spiral state. And we can quantify this by taking light section, we get this sinusoidal behavior. And in fact, we confirm this in collaboration with Vincent Jacques by scanning NV macroscopy, where there is no magnetic tip. We get exactly the same periodicity for the spin spiral. And very interestingly, the expression of the periodicity is very simple for spin spiral in SAF, because as you see, it's equal to the ratio of the exchange interaction, the exchange stiffness parameter, over the Jarus-Schema interaction. And as we can measure the Schema interaction, we can then extract from this periodicity the exchange interaction in this thin film, which is a parameter that is very important, but not very easy to quantify. But then we want to have antiferromagnetic scarments, not only spin spiral. And for that, we integrate again this bias layer, symmetric platinum cobalt platinum, in the systems in order to make this effective magnetic field that will be filled by the bottom layer of the cell. And doing so, we can predict by simulation that it will transform the spin spiral into antiferromagnetic scarment. And this is what we, in fact, did, and we demonstrate, again, by MFM images at room temperature under vacuum. This is, to my knowledge, the first observation of antiferromagnetic scarments. These are these black dots here. Maybe it's hard to see, but if you make some line section, again, across different of these black dots, you do see that we have a signal, that the amplitude of this signal, the contrast is about 1 degree, where when we make the same images on the ferromagnetic scarments, we can measure 10 degrees. So this is already a signature that we do image antiferromagnetic scarments, so very weakly magnetic scarments. And the radius we find is about around 50 nanometers. But in fact, if we take into account the role or the interaction with the tip, then we deduce that the real diameter is probably closer to 20 or 30 nanometers. This was done by MFM under vacuum, but there have been some also some study by this NV scanning NV microscopy by Finco and Vincent Jacques from Montpellier, and they find exactly the same type of structures, which have been imaged in a new mode for the scanning NV magnetometry called spin relaxometry. I have no time to speak about that today, but this explains why we get some contrast in photoluminescence above these scarments is related to the magnetic noise that is associated to the scarment. But everything can be found in this publication. Okay, so I don't know how many times I still have, but I would like to finish this seminar by showing very recent results when we now we want intentionally to go toward 3D texture, 3D spin texture. And this is not only us that have this interest, but there are several groups that have started to look at more complex spin texture, like bubbles that have been observed, predicted and observed in non-centrosymmetric bulk materials, iron germanium in Jülich. And these bubbles, you see, they are like a cut. If you cut the scarmion tube, but then you have a block point, okay? And there are other type of structure like globules, or even a new family of topological spin texture that are called the options, okay? And this is typically the kind of structure we would like to study, again, by using our platform and expertise in the preparation of multilayers. So for that, we use multilayers, but this time, where we vary one parameter. We started with a simple one, that is, we vary the thickness of the magnetic layer within the Z direction of the multilayer. You see, we have here a variation of the cobalt thickness, and this is what we call the gradient structure. This work is a PhD work of Mathieu Grelier in our lab that started about 1 year. So we can prepare a block, what we call gradient structure, and look at, this is Mathieu Grenier, look at the magnetic configuration. So again, we use MFM. This is a typical configuration that we do have after in-plane demagnetization. We have strike domains. And then we have out-of-plane demagnetization. We have a very dense phase with scarmons, even scarmon lattice phase. You see, we do have some ordering of the scarmons. But then, interestingly, when we go back to zero field, we see that we keep, okay, we have some elongation of the individual scarmons, but we do keep a structure with isolated spin texture. And this is contrary to what we generally observe, as I showed you before, in, let's say, regular multilayers, where we have a straight domain or a labyrinthic domain at zero field. We can quantify, measure, make some statistics about the mean diameter or the density of scarmons that we can measure. But then we can go beyond and prepare more complex stackings, more complex heterostructure, by using two of these blocks, two gradients multilayer, and separated by some multilayer with perpendicular, large perpendicular magnetic anisotropy. Okay, and then to look at what happens. And these are very recent images that we obtained by MFM. You see that after the out-of-plane saturation and go back to small field or zero field, we clearly have two contrasts. This is more seen here, where we have a demagnetization with an angle. We have these stripes in red, and then in between the stripe, we have this white structure that corresponds, demonstrate that we have two types of magnetic configuration or magnetic texture in the multilayers. Then, when we increase the field from the zero field imaging, we do see these very nice systems with two objects, and that end up with a large magnetic field with these two things that are in red here, what we believe are scarmon tubes, okay, that are going through all the multilayers. And then we have this white spot that corresponds to localized three-dimensional spin texture in the volume of the multilayers. And this is confirmed by micromagnetic simulation that we have performed recently. So these are a representation with all iso surfaces. So in red, you have a MZ value equal to, in this case, I think it was -0.9 or -0.8. And in white is MZ equal to 0. So you see that at zero field, we have some warm structure that goes throughout the multilayer. And then when we do increase the field, we keep two types of objects, either this columnar scarmion, let's say, tubular scarmion texture, together with these cocoons, what we call cocoons. So they are kind of squeezed tubes or tipped tubes, and that are present only in one part of the multilayers. And in fact, this was by MFM, so we are sensitive only to the stray field coming out emerging at the surface of the multilayer. But we use recently, in collaboration with Nicolas Jaouen and also Félix Butner, a measurement at Soleil, this X-ray holography technique, where we use a coherent X-ray beam, shine onto an object, but also at the same time a reference hole, and we can collect on the camera the interferences, the hologram with a resolution, which we can reconstruct the magnetic configuration with a resolution about 20 nanometers. And this is a movie that what can be obtained by varying the perpendicular field. You do see clearly, and now we are, importantly, we are sensitive to all the systems because we are in transmission here. So you do see that we have different objects, two different contracts very quickly, clearly. And interestingly, we can also start to have a look on the way these cocoons, that we believe are the cocoons here, they can merge together in order to end up and basically finish in being a scanning tubes. Okay, for that, I think I'm reaching the end of the time for the seminar. I hope I show you that there is a lot of very interesting physics to do with the scarmions, but also other spin texture that can be stabilized at room temperature. And I do show you that we have some results in either ferromagnetic multi-layer, so kernels can be very small, can be very dense, can be stabilized zero field. I have no time to speak about that today, but we do have in the postdoc of Titikcha Srivastava some resonant dynamics of these kernels. I show you also that we can have a system of kernels in a compensated magnetization systems, anti-ferromagnetic systems, but also ferromagnetic systems. And finally, that we can push this engineering and the control of the property in the multi-layer for the stabilization of more complex and with a lot of still questions about 3D spin texture in the multi-layer. And with that, I thank you very much for your attention. I would like again to thank you, all the people working in our group and all our collaborators, and also the different agencies for the funding to support this work. Thank you very much.
Yeah, thank you so much, Vincent, for this wonderful lecture. I congratulate you, and on behalf of all the participants, I really thank you for your excellent lecture. We all enjoyed. I'm sure there will be many questions, but as I said, we will first take a small, quick photo. So if you could kindly stop sharing the screen.
Yeah.
I request all of you to switch on your camera. Yeah, thank you. So I request all of you to smile. Yeah, there are more people. Okay, so thank you. So we can switch off our cameras now, and I request Manso again to share your screen.
Okay.
So let us begin the question answer session. So I see already there is a raised hand by Ankit Lav. Ankit, please ask your question. Please unmute and ask your question. Oh, you were just clapping. Okay, I'm sorry, I misunderstood. Then let me ask, so in the multi-layer where you are taking the aluminum as a, like a, yeah. I think top layer. So what is it just because to incorporate some kind of Rasba coupling into it, or what is the motivation behind that?
Okay, to tell the story, I mean, what we try to do is obviously to improve the motion, the dynamics of this kernel by this spin orbit torque effect. And initially, we wanted to have to use systems with a double, let's say, spinel effect injector, like platinum, cobalt, and tantalum systems, because the tantalum and platinum, they do have opposite spinel angles, so you can create, convert, and create spin current. We'll have an additive effect from the two elements. But if we, when we try to do this, we realize that from the growth point of view, the quality of the interface between cobalt and tantalum was not that good. And that's why we first integrate aluminum, because this is a light element. And this, at least we have that in mind, should allow to transfer properly the spin current from the top tantalum layer into the cobalt. Okay? But then we realize that it's much more than that. It's not just the aluminum, it's not just a spacer layer. It's a very interesting layer to be integrated because, as I showed, thanks to quantitative determination of the spin orbital, we do find that the aluminum brings two effects. First, it makes that when it's relatively thick enough, talking about more than about 3 nanometers, then it's in fact the transmission of the spin current from the tantalum to the cobalt is killed, and contrary to what we initially thought, so it kills the transmission of spin current. And second, there is a very strong Rashba state that takes place at the cobalt aluminum interface, which creates, which gives strong contribution to field-like torque, but also an increase of the damping effect. So the integration of aluminum gives directly three different, very interesting effects in this multilayer. I hope I
thank you.
Part of your question.
Who has questions now? Any questions from the audience? Please raise hand or unmute. Yeah, Professor Borman, please kindly go ahead.
Yeah, thanks a lot for a very nice talk. I just wanted to know that what is the possibility of, because I know that these Carmion lattices can be used as a kind of on-demand magnonic crystal. So for that, one has to, arrange them, and like you presented in one of your slides as Carmion a la carte, like you can tailor them in different lattices, change the lattice constant, and so on. So what is the possibility of, this, of doing this at will?
Thank you very much for this very good question. I would say it's a pity because the time today didn't give me the opportunity to speak in detail about what we did in the postdoc of Titikcha Srivastava together with colleagues from SPEC and C2N. We precisely study the resonant dynamics of Carmion lattices in multilayer. You can find, I make some advertisement, all the information in this paper that we recently posted on the archive. The main result is that in this system, so there are these very similar multilayers, and we find that we can determine the Carmion modes. We have different modes, let's say, that are associated to the presence of the Carmion lattice phase, and we might have either some modes corresponding to motion. I mean, some modes inside the domain walls around the Carmion walls. Okay, these are relatively low frequency, but then interestingly, and I think for the first time in this multilayer system, we do find at higher frequency in the range of 10 gigahertz, a mode that is associated to the presence of Carmions, not connected in the sense that can be considered as magnetic crystals, because for this mode, in fact, each Carmion is a spin wave emitter, but there is a kind of resonant effect or amplification effect of this spin wave emission by the individual Carmions due to the periodic arrangement of the Carmion in the lattice. And this is where the property of this mode in the around 10 gigahertz in this metallic multilayer can be associated to the property of the Carmion lattice. We are at the very beginning of the study because this is the measurements are relatively complicated, and that the way to control, let's say, the property of these magnetic crystals is probably not that straightforward, in the sense that it's not probably only sufficient to change the periodicity of the lattice, let's say, in order to control. It will change the property of the crystal, the magnetic crystal, but it will not allow to control the frequency, for example, range where we do have a gap for the spin wave transmission. But please have a look on this recent paper, and if you have any questions, you can contact me. I will be happy to answer. Thank you.
Sure, I'll do. Thank you so much.
Yeah, thank you so much, Professor Borman. Any other question by anyone? If not, then maybe I can ask one more question. So in the beginning, you showed the results from the platinum cobalt iron boron, and you showed the Carmions were like less about 20 nanometer. So what is the origin behind these very small Carmions? I mean, is there any other interface engineering has been done, or it just came like that?
No, it's as I said, I mean, in these systems, let me go to, in these systems, the property of the Carmions is really the results of a very fine balance of all the magnetic interaction in the multilayers. I'm talking about exchange interactions, anisotropy, interlayer interactions, dipolar fields interaction, I mean, interlayer dipolar fields. And the property of the skyrmions is really the results of a fine balance of all of that. And this is in these systems that, let's say, we push the change or the control or the modification of the indie property up to the maximum. And this is probably why we reach in these systems the smallest skyrmions that we can up to now image. Probably we could do similar things with the other system, but it requires you see a lot of optimization of the different parameters.
Yeah, I mean, thank you. But my question was, is it like the ruthenium just on top of cobalt iron boron and below platinum is somehow helping that to make?
Yeah, the ruthenium. I mean, what you need is to have two different materials, because if you have symmetric elements around the magnetic, then you have no geosystemary interaction, and so you cannot stabilize those skyrmions. Ruthenium instead of other ones is because, at least in our switching machine, we succeed to optimize the system, and this is basically you remember the same that is used for the synthetic antiferromagnets, to get the very good values, the quality of the films, the quality of the interfaces, and the fact that we do have a sizable DMI interaction coming from this cobalt iron boron ruthenium interface. So, but this is just you see, this is a question of, again, material science and material property. It looks like the cobalt or cobalt iron boron ruthenium interface is quite good and very good, so it allows to make very nice stacking of magnetic materials.
Yes, thank you. It's very exciting. Yeah. Questions by anybody else? Okay. All right. So there is somebody like Ankit Lab. How do you see future of hafnium in spintronics?
Future of, sorry?
Hafniums.
Options.
Yeah.
I mean, how can I see? First, I would like to see them. So, so this is what we are currently trying to do. And no, I think the options are, I believe, any other type of three-dimensional spin texture. Options, they are objects with a specific topological properties, but we can think, and this is where we start to work with this three-dimensional spin texture to have like maybe three-dimensional like spheres, that can be stabilized in the material systems. It's probably we are really at the early stage, but it's a way to project all the good property of the skyrmion in two-dimensional media into the third dimension, and this is where we can make. Thank you very much for this nice thing. We can start to imagine some concept of devices that will be purely three-dimensional, and this is a very challenging objective in spintronics, but not only in electronics, to go from 2 dimensions for the 2D systems to 3D systems, because for example, in the perspective of trying to go for neuromorphic type of applications, if we want to mimic the brain, in the brain we do have a lot of interconnection, but not only in planes. You have interconnection between planes in all the direction, and this cannot be simply achieved if you are stick with only 2-dimensional quasi-particles, like can be the domain walls or the magnetic field. So this is where it's very important, also very interesting to go for the third dimension. As far as application, real devices and application are concerned, I mean, it's really the early stage of this research, and I think we still have to wait for a little bit before making some claims about when we will be able to buy like options-based device.
Yeah, thank you so much. I think we really had a very interactive session. On behalf of everybody, I like to thank you, Hansa, for this excellent lecture and showing your very latest new results. We are really looking forward to the papers. So on behalf of the WTS team, I like to present this digital plaque. So as you said, it would be actually our more pleasure to have you in our campus, to show you around. It's a very beautiful place. And hopefully in a year or so, maybe we can make travels and we will be able to welcome you. So nevertheless, I like to read this plaque for you. So WTS Seminar Webinar Series on Spintronics, Nice Sir, Bhubaneswar, India, takes pleasure in presenting this plaque to Prof. Vincent Cros from CNRS Thales in France, in recognition and appreciation for being a very valuable speaker to give a lecture on non-collinear 3D textures in magnetic multilayers from hybrid chiral textures to Scormioni cocoons. So thank you so much, Vincent.
Thank you very much. Thank you very much. Thank you very much. I really appreciate for this plaque. You know, I'm not professor. I'm working at CNRS, so I'm not a professor of the university. So, but this is really, thank you very much for the.
Thank you for your talk. Just to advertise, next week we will have the lecture by Professor Yoshihiro Otani from Riken in Tokyo, Japan. So I hope to see you, some of you, or all of you.
I'm sure it will be an excellent seminar.
Yes, and so please stay safe, all of you, and see you next week. Thank you so much, Master, for this excellent lecture. Thank you. Take care. Have a nice day. Bye bye.
Have a nice day. Bye bye. See you.
Bye.